The topic of the paper I will present today is Design of Intelligence Integration System for Multi-Source Industrial Fire Database on Machine Learning. I will divide into 4 sections: motivation, contribution, methodology, and system test. First, let me explain the motivation. The motivation for designing the multi-source industrial fire data intelligence integration system based on machine learning is to address the problem of scattered and difficult to manage information in the current integration system. The traditional data integration system is labor-intensive, time-consuming, and ineffective in reflecting the real-time situation of production, which hinders the improvement of the enterprise management level. The existing intelligence integration system based on TRS network data radar and web spider software have limitations in terms of data search accuracy and price. Therefore, the proposed system aims to provide a more efficient and cost-efficient solution for enterprises to centralize and utilize real-time information from various links of the production process, thus improving the overall production and economy performance of the enterprise. Next, I will introduce the contribution. Our research demonstrates the design of a multi-source industrial fire data intelligence integration system based on machine learning to address the challenge of scattered and difficult to manage information in the current integration system. Additionally, we utilize machine learning-based host technology to integrate on-site data and design an intelligent retrieval engine for on-site data to provide an integrated environment for users' data processing. This was completed by the design of data integration channel, point-to-point circuits, independence power line selection, impulse noise removal, and visual data integration. Furthermore, we identified a need for further research to enhance the essence of machine learning to adapt to the changing multi-source industry fire environment, particularly for frequent disturbed combined network attacks. Finally, we address the data technology structure, use the database connection pool technology to integrate fire data, and check the integrity of the integrity data. Next, the third part is the method. I would like to divide these parts into 2 subsections to introduce. First is the system hardware structure design, and the second is the key technology research of the system. Let's start with an overview of the method first, which is a machine learning-based method for intelligence integration of multi-source industrial fire data to ensure efficient operation of multi-source industrial sites. In order to increase the capacity, multiple additional cables were laid, increasing the fire data and making it necessary to integrate the data. The system consists of 5 layers, namely the software support layer, the integration bus layer, the data bus layer, the service layer, and the application layer. The software support layer includes the underlying communication components for multi-source industry fire operation. The integration bus layer provides a standard illustration mechanism for multi-source industrial internal modules using a common object request agent architect. The data bus layer is responsible for connecting data platforms and database access interface and data interface. The service layer can meet the platform interface for each application requirement and realize the relative independence of the service layer and market business. The application layer provides the application service interface required for the market operation. The system serves as a platform for industrial market data information demonstration, integrates relevant real-time data, determine coupling relationships, and play a role in data sharing. The following four components are described in the system hardware structure design section. Multi-source industrial fire data synchronization unit. The components is used to integrate fire database system using middleware technology. It consists of four components: a concentrator, adapters, metadata and management configurations, and a web server. The middleware is built between the database service system and the application, forming a three-tier client service aggregator. Intelligence search engine for fire data. This component uses machine learning technology to integrate fire data. It consists of four components: data search, data index construction, data sortage, and user interface. The retrieval engine uses machine learning-based host technology. And the third part is integrate channel circuit design. This component uses a crystal oscillator as the core, a balanced circuit of capacitors and inductors, and a whip antenna to transmit and receive wireless data. The point-to-point circuits for the data integration channel is designed using the ST-80500 programmable power line communication system on a chip as the core system for the modulation and demodulation module. And the fourth part is real-time database construction. These components provide efficient data sortage, complete information query, and real-time transition operations, and is the basic union of the real-time basis. The real-time database places time construction on data objects in transitions and performance transactions scheduling to improve the transition throughput of the system. By the way, real-time database systems are used for efficient data sortage, information queue, and real-time transitions. They have the following characters. The first is time constructions are imposed on data object and transactions and temporal consistency requirements must be met. Transaction scheduling focus on completing transactions within their deadlines, and scheduling stressors process transactions. And the third is real-time data storage management is important, and the database should occupy a small space in memory to ensure fast access and easy data sharing between function modules. Functional modules of a real-time database should include initialization, basic operation, read and write data operation, communication device, read or write operation, window operation, alarm operation, and save operation. These modules provide basic operation for data objects, communication device, user window, and alarm information storage. We present the study of the key technology of the system in the section. The key technology research of the system, in particularly a machine learning network based on Bayesian probabilistic general active model. The network consists of Bohr's domain sets for integrate task scheduling based on machine learning. Task schedule involves unsupervised training and tuning, and the network is trained locally by modifying the 8 parameters, which makes the network efficient and fast. An integrate task scheduling model is developed, which includes an auxiliary variable that generates a loss queue representing the difference between the actual current revenue of the system and the target. Adjustable parameters were introduced to control the balance of system revenue and system latency, and resource clustering algorithm was used to cluster resource and general scheduling task queue. Resource queue are assigned accurately and randomly, and a property auxiliary resource are selected for queue. The alignment of the date is also discussed, which is involved the formation of date mapping table for multiple sources of industry domain date. This mapping table is an important connecting bridge between offline and online data, which facilitates the maintenance of multi-source industry fire data. The mapping data includes a date mapping table combined with timing characters, a fired device mapping table, and an AC line mapping table, and a line mapping table. The verification of offline and online data is done based on the mapping tables. We will not go into detail in today's representation due to the time constraint. Next is the experiment, which is this part of our system test. We present experiment conducted to test the performance of a machine learning-based intelligence integration system for multi-source industry fire data. The purpose of the experiment is to compare the data integrity of the system with a TRS network data radar-based integration system and a web spider-based integration system. The experimental environment is the same for all three systems, with the same hardware and software component and the same simulation software. The integrity system platform is a platform for monitoring violation of system safety principle at multi-source industry sites. The platform's data source provides monitoring data, and the analyze engine is representable for analyzing and reviewing the data. Once an abnormal integration result is detected, the data is immediately transformed to the response module to generate feedback information. The experimental indicators used to evaluate the performance of the system are the accuracy rate and record rate of the data integration results. The formulate for calculating the accuracy rate and record rate are provided in equations and equation 40 and equation 15. The larger the calculation result of the formulas, the more accurate the inspection results are. In order to ensure the authenticity and reliability of the experimental results, the experiments are cross-validated several times by comparing and analyzing the experimental results. The effectiveness of the integration system of multi-source industrial file data based on machine learning is determined. In this part, we analyze the data integration effect of the multi-source industry file data integration system based on machine learning. We compare it with the integration system based on TRS network data radar and the integration system based on web spider. We use accuracy rate and recall rate of data integration results as evolution criteria. The comparison results are shown in Fig 6, which demonstrate that the data integration effect of the machine learning based on integration system is better than that of other two methods. In addition, we conduct a data integration integrity checked by setting three external interface conditions: buffer overflow, running process, infection, and children hosts. We select two experimental sets and train them to get the ROC curve. The results are shown in Fig 7. It can be seen that the accuracy of the data integration results of the machine learning-based integration system is always greater than 0.95 when the record rate is greater than 0.40 under the two interface conditions. This indicates that the machine learning-based integration system can obtain fully integrated data. Yeah, this is our report today. Thank you for listening.